Good evening, Manada. Welcome back to the video lecture series, Signal Systems. This is Dr. P.C. Vaslu. Today, we are going to discuss about effect of undersampling. Nothing but aliasing. Now, the sampling, according to the sampling theorem, whenever we are going to be convert a continuous time signal into a discrete time signal, there is a three sampling cases. First case is minimum sampling rate. Fs is equal to 2fm. The derivation already we have seen. Now, suppose if we take Fs is less than 2fm. So, at least it is less than the minimum sampling rate. That is less than the sampling frequency, whatever we have chosen. It is not satisfied the minimum sampling rate. If you not consider minimum sampling rate, what happens? It is called undersampling, or it is also called aliasing. So, you see this one, this diagram. We observe this diagram. The x of f is original spectrum and x delta of f is sampled signal spectrum. Now, in this sampled signal spectrum, we know the formula. It is a periodic spectrum with fundamental frequency Fs. So, the highest frequency component is here, W. That is nothing but Fm. You can, in this data, whatever it is like a W. Now, we can also call it as the maximum frequency W. So, Fs is equal to less than 2W. Fs is equal to less than 2W. If you choose like that, suppose W is equal to 1 kHz. If you choose Fs is equal to, at least for sampling frequency, we require 2 kHz. But if you choose sampling frequency 1.5 kHz, 1.5 kHz. Now, if you observe this spectrum, in this spectrum, first one, as usual, in the formula, summation of n equal to minus infinity plus infinity, Fs into x of f minus nfs. Whenever if you substitute n equal to 0, the original signal spectrum and the sampled signal spectrum, both are same, but it is multiplied with sampling frequency Fs. And then, if you observe clearly, the Fs have selected less than 2fm. That means, for example, for our understanding purpose, this W is equal to 1 kHz. Have chosen this Fs is equal to 1.5 kHz. Whenever this n equal to 1, in the formula, it is a delayed spectrum. This center one is going to be get at Fs. This Fs is 1.5 kHz. Now, the upper side band is 1.5 kHz plus 1 kHz, means 2.5 kHz. This lower side band, 1.5 kHz minus 1 kHz. So, it is a 0.5 kHz. Already this one at 1 kHz, this lower side band of second spectra is 0.5 kHz. There is a overlapping of spectrums from the frequencies 0.5 kHz to 1 kHz. So, the high frequency is mixed with the low frequency. It is going to be appear like a low frequency. It is called aliasing. This shaded region is called aliasing. So, because of this aliasing, we are going to lose some information So whatever the losing information, it is not going to be retrieved at the receiving end. So that is the problem of undersampling. So like that, if we consider all the spectrums, delayed or advanced spectrums, so there must be a overlapping of these spectrums. So whenever it is a overlapping, where it is not possible to reconstruct our original signal. So the main motto of sampling is here, we are not fulfilling. So that is the problem with undersampling. Now, you see the conclusion here, the spectrum located at x of f minus fs, x of f minus 2f, or x of f plus fs, x of f plus 2fs, and so on, the overlap each other. Next, consider the spectrum of x of f and x of f minus fs shown in the magnitude in the above figure. The frequency spectrum from fs minus w to w, whatever I have explained with 1 kHz, so that is overlap. So finally, aliasing means high frequency interferes with low frequency and appears as a low frequency, then the phenomena is called aliasing. So what is the effect of aliasing? What is the effect of aliasing? Now, whenever at the receiving end, it is not going to be reconstruct our signal. Next one is, whenever if you take oversampling case, whenever if you take oversampling, Fs is greater than or equal to 2W. Fs is greater than or equal to 2W. Now, whenever Fs is greater than or equal to 2W, it is greater than the minimum sampling rate. There is no problem at all, because suppose W I have assumed 1 kHz, Fs is greater than 2W means greater than 2 kHz. So Fs I have selected suppose a 3 kHz. So the spectrums we are going to get, this is a 1 kHz, 3 kHz plus 1 kHz, 4 kHz, 3 kHz minus 1 kHz, 2 kHz. There is a guard band also there. There is a gap between these successive spectrums. So to avoid aliasing. So there is no any overlapping. So we can easily reconstruct this sampling case, because we can pass this spectrum through a low pass filter, practical low pass filter, and then we can reconstruct that one. Now you see this one, a band limiting signal. A band limiting signal means what is the x of t that is strictly band limiting to a low pass filter. The low pass filter we are designing with what is the signal we have. In that signal, we need to find out the Fourier transform, and then what are the frequency components present in that signal. So we identify the frequency components, and the highest frequency component we need to notify, and then you pass the signal through this one low pass filter. It is strictly band limited to FM, and then we go for sampling. Now, it is another very important thing, Nyquist rate. Nyquist rate or Nyquist interval. Before class also, I explained a Nyquist rate means a minimum sampling rate. Nyquist rate means minimum sampling rate. So, at least you need to select the Fs is equal to 2W Hz. Or Nyquist interval means Ts is equal to 1 by Fs. If you know Nyquist rate, you will get the Nyquist interval. Now, we need to reconstruct our original signal. So before going to get reconstruct the original signal, we need to reconstruct the original spectrum, and then we apply inverse Fourier transform, you will get the original signal. Now, if you take an ideal filter, ideal low pass filter, ideal low pass filter means it has a sharp cutoff frequency. It is like this. If you see, it is a ideal low pass filter. Now, the highest frequency component is W, and whatever the frequency components, what are the frequency components? The frequency components are strictly band limited to this W. Now, if you observe this one, this type of frequency response, practically it is not going to be possible. It is only a theoretical case. It is an ideal case. So, through this filter, low pass filter, if we pass the spectrum, whatever the frequency components from minus W to plus W, it is going to be allowed. Remaining all spectrums, it is going to be rejected. It is the ideal low pass filter output. So ideal low pass filter output, again we are going to get this shaded ring. Now if we observe this much of cutoff frequency in practical cases, it is not going to be get. So, and then if you go for practical case, non-ideal filter, now if you choose the sampling rate, Fs is greater than 2 FM, the spectrum is like this. And then if you consider a practical low pass filter, if you observe here, there is a transition is takes from high to low. This type of filter we can easily implement. And then if you pass this spectrum, Fs is greater than 2 FM or Fs is greater than 2W, and then it can be easily reconstructed. So it is the practical filter. It is the ideal filter. Okay. It is about sampling theorem of low pass signal and its concept. I'm going to stop this class. We will see in the next class with another topic.